Okay. Welcome. Yeah. So, welcome to our lecture on Wednesday. We're gonna delve into chapter 7 in a moment. Let me just get the zoom up to make sure. Okay, so I can see the chat. So if you do have questions, feel free to pop them in there. Things you might be curious about. So I've made my way through your exams, and I am just crunching the last few details before I post those. So your grades will be posted to Canvas probably later this evening, unless something comes up, and in that case it'll be in the morning. So I think I have a way to kind of display each of the individual questions. So they'll show up as 5 kind of sub-grades, or it's listed as 5 separate assignments in Canvas. So you might, on your grade book, you should see, Q1 midterm 1. You can't see it right now, but you will see Q1 midterm 1, Q2 midterm 2, and so on. And that I think is the easiest way, or the most straightforward way, to give you the individual grades on each question. That way it'll give you some insight as to where you might have lost some points. I'll also have the solutions posted, so you can take a look there. Please look at those, even if you got everything, or if you got all the points on a certain question. I may have approached it slightly differently, or you got it pretty close, and close enough that I didn't take any points off, or I thought your train of thought was valid. But take a look and see. We'll just call that good enough. You can peek at the way that I approach those problems. And then the other thing to remember is to take a peek back at the syllabus, where I outline kind of how the grading structure will go. In that, to reiterate just a little bit, there's no defined percentage. So if you get a certain percentage, that doesn't equate directly to a certain grade. And I know that's a little different than, especially for a freshman. I think typically in high school that's a more typical way to grade. But as we've talked about, that's not quite how it works here. And of course that can, we won't get too much into the weeds, but just know that. So what I will email out is kind of a breakdown as far as, okay, so let's say on Canvas it says you got a 37. What can you expect that to be, as far as if you wanted to put that more in a letter grade? So look for that in the email as well, at kind of the same time that the grades are posted. So and overall, I thought people showed good understanding, and I will, either Friday or next week, we may just chat about a few concepts that we'd like to see, or maybe I need to clean up a little bit. Okay, so what are we doing today? So today we are turning to chapter 7. Now chapter 7 is all about continuous probability distributions. Now, there's two big goals we want in chapter 7. The first one is to understand continuous probabilities, and that's going to mirror what we did in chapter 6. The other big goal to keep in mind is that we want to get a good grasp of the normal distribution and what it is and how we go about using it. So we'll set aside the normal distribution for a moment. I want to just kind of highlight that much of what we're doing here, where am I on the screen? Okay, so in chapter 6, we dealt with discrete variables, discrete random variables, right? And we had discrete probabilities. And the key about those, one way to think about it is that we count, right? It's falling on a defined number of values. Oftentimes these are integers, so if we actually are counting something up, right, the number of free throws that you've made is, you either make 1, 0, 1, 2, 3, 4, 5. The number of credit cards in your wallet, the number of limbs you have, right? These are all defined these are all integers. Now, as I've pointed out, it could be something like how many cups of flour do you use, and if it's defined as 1 cup or 1.5 cups or 1 1/3, those can be discrete as well. So we could think about looking in a let's say you have a recipe book and you want to flip to a random page. What's the chance that there is 1 3/4 cups of flour used in that? That can still be a discrete because we have a very fixed number of possibilities, right? It's either going to be 1, 1 1/3, 1.5, and so on. So I just want to point out that can be discrete as well. What did we do with our discrete situations? We wanted to characterize the situation, okay, the different probabilities of the different outcomes, right? We have an experiment. We have all these outcomes that fall on some integers. We summarized that with the mean and the standard deviation. We also depicted it, right? So for I think the free throw example looked something like this. And we depicted, well, that's not enough. 1, 2, maybe there was one here. I don't know. But each of those had a defined value at the discrete value, okay, or a defined probability at the discrete value. But that was our process. We summarized it with the mean and the standard deviation. We then depicted it. And in general, what we did is, well, so we talked about the general sense of discrete variables and discrete probabilities. And then we worked our way to some specific kind of family or classes of scenarios. So we spent most of our time in the binomial. Okay, so we had this general concept, some of the math that applied to the general concept, and then we worked into the binomial and walked through kind of some of the shortcut math that we can use, and why we talked about why the binomial shows up so often, in that we can turn a lot of things into the binomial. And remember, there were other ones. So I just had you read through. You don't even have to do any of the work on the hypergeometric, but that existed as well. So there are other specific classes. So in the case of continuous, where we are in chapter 7, our workflow is going to be the same, or it's very similar. It's going to look much like this, okay? So we are going to want to, when possible, calculate the mean and the standard deviation of our distribution. We're going to want to depict it, okay? So we're going to want to put it on a graph. The way we interpret it and the way we do that is slightly different. So we're going to want to do that. We're going to want to draw it. We're going to talk about the general, okay, the overall kind of concept, and then we are going to spend some time in the specifics. Okay, but these are just a couple of the different specific family groups, much like the binomial and the hypergeometric, where we have some specifics. We're going to talk about the uniform and the normal. Okay, and this is where we're going to be reintroduced to the normal distribution and spend a lot of time there. There are other ones. Actually, the book has an area on exponential, which I've mentioned you can skip for sake of time. But if you are interested in that, please feel free to look through it. So our flow is going to be the same. Hopefully that's kind of clear that we're doing the same process. We want to get the same, we want to have the same abilities to summarize the distribution in front of us. Now, the big difference, discrete, continuous. We were introduced to continuous in chapter 6 when we talked about discrete, right? So these are things you're counting. One way to think about this, continuous, is, are we measuring something? Okay, that's a kind of a broad way to summarize it. And when we measure things, we often have more precision in what the exact value is. And that's really the big difference, is how precise are we? So these are all going to fall on very oftentimes integers, but they fall right on an exact value. Continuous variables, it can fall anywhere along a range. So the whole number line is available. And in theory, we could be anywhere along the value. So if we had a recipe book that you could think of this as measuring in cups, or flipping to a page and it says 3.5 cups. If we instead, when you get, I think, fancier into cooking, you deal with grams, right? And so there's a little more precision there. And so there might be a recipe that says 37 grams and another one that says 38 grams. And so we start to get into more of a continuous stretch. Let me shift gears a little bit and let's think about, we're approaching winter. I think it might freeze tonight or tomorrow night. How much snow are we going to get this winter? So we don't know. There's an experiment here. We don't know what the outcome is going to be, but it's going to be somewhere across a range, right? It's probably going to snow more. We could put like kind of bounds on this. It's probably going to snow more than 30 inches, and it probably won't snow more than 130 inches. It's going to be somewhere in that range, but we can be pretty precise when we measure snowfall. So we could think about 65 inches, but because we can measure snow, so we could have snow of 65.000, we could have 64.999998, 65.001. I don't know exactly how precise they are, say at the airport or wherever our best measurement is at. But whatever the level is, we could think that, or we know that it could fall anywhere in there. Okay, so what are the odds that it actually falls right on 65.000? It's essentially 0. The probability is 0. Okay, so in the discrete case, we have defined probabilities that it's going to fall on each of these values. Here we don't. Okay, so what's the probability that it falls right on 65.000? It's basically 0, right? And it becomes 0 if we give even more precision, right? So I'm putting a little bit of a constraint here and saying we're measuring to the thousandth of an inch. But really it could be 65.00002 or something, right? We could keep getting more and more precise. And when we do that, it's no longer even just basically 0, it is 0. So the probability of falling exactly on any value in a continuous distribution becomes 0. So all of these are basically 0. Okay? And I'm being a little fuzzy because, of course, it's going to fall on one of these because we're not being that precise. But we can treat them as basically 0. So that becomes a problem when we want to talk about the likelihood of certain outcomes. Because if we wanted to draw that, if we wanted to draw and depict all these probabilities, we would no longer have any height. These are all exactly at 0. Right? Every value I pick is right at 0. So that's not very helpful. So what we're going to talk about instead is ranges of outcomes. Not just a specific value, but a range of outcomes, or a range of values. So it's somewhat related to, at the end of chapter 6, we briefly learn, and it's okay if this, you kind of skimmed through this, because we don't talk about it too much, but we talk about continuous, the cumulative probability distribution. That being, of course, in this scenario, we can talk about the probability of 3. We could talk about also the probability of greater than 3, or greater than or equal to 3, right? And the way we did that is to say that's just adding up all of this range. So it's the probability of 3, 4, or 5, right? We did this in the free throw example. What's the chance that as a 70% free throw shooter, you make at least 3. So we did that. We could also think about the probability of 3 or 4, right? And that would just be adding up both of those. So we've already started to go down this route of ranges, right? This is really the range between 3 and 4. So that concept isn't that new to us. So next what we're going to do is apply that to the continuous distribution. So instead of thinking about the exact value of, say, 65 inches, what if instead we used a range and said, okay, well, what's the probability that it's between 64.5 and 65.5? Now we have a range of outcomes, which includes all of these intermediate points. Okay, so this includes 65.66666666. It includes 65.77777, and so on. All of the points in between. So now, each of these individual numbers has still a probability of exactly being 0, or it being exactly that of being 0. But we can talk about the range in between it. Okay, and so graphically, that's going to be an area. So this hopefully will sink in more when we look at some full distributions. So we can think about 64.5 to 65.5. We could do any type of range. We can do, what's the probability of 65 to 65.04? Okay, it's a very small range, but as long as there is a range, we can calculate it. So the way we depict these are going to be a little different. Okay, so I'm going to erase this, and I'm going to draw a probability distribution for the snowfall. Okay, and I have no idea what this actually looks like, but let's say that it looks, I don't know, we'll pick something like this. Okay, and maybe there's some, this is, I have no idea. This is El Nino causes it to push it this way, and there's probably reasons why it's not a nice clean one. But let's say that this is the distribution of snowfall in Minnesota, and it's down here is this is probably not accurate, but maybe this is near 30 inches, and again this is like 120. Pretty unlikely. Although I lived in Madison one year and we had 108 inches, so it is possible to get up there. Okay, so what we're really talking about is, so each of these values by themselves has a probability of 0. It still remains true that at 65.00000000, there's no chance that it falls exactly there. Or theoretically, there's no chance there, okay? But when we talk about a range, if I want to say 65 to 70, this is now an area that I can calculate, and that area is the likelihood. So, how is this possible? Well, jump back to discrete. If we add up all of the probabilities here, remember what they sum to? They sum to 100% or 1, right? That has to be true. If we're going to depict a probability distribution, it has to be collectively exhaustive. Every possible outcome needs to be shown, okay? That means, in our case here, if there is a possibility that goes to that 130 inches, we need to include all of those probabilities. Even if they're very small, it needs to be included. So, the sum of all these equals 100, or 100%, or 1.0. Same thing is true here. If it shows up, if it's possible, it needs to be depicted here, and the sum of this whole area is 100%. That's going to be an important thing to keep in mind, and it's going to be a tool that helps you, get through the problems a lot easier if we can remember that this is always going to sum to 100%. Okay, so any sliver that we take out, you can think of it as a share of that 100%, or it's a part of that 100%. So from 65 to 70, there's a chunk out of here. Maybe that's, 14%. So that's 0.14. Everything outside of it would be then 0.86. Okay, so the whole thing has to be 100%. It's all the possible outcomes. Of that 100%, 14% fall in this window. We can draw any type of we could pick 92 to 92.3. Okay, we can draw little tiny ones in here. Okay, and we could calculate the area of that curve, or that bar there. Now, how we go about calculating that is rather cumbersome, depending on the type of distribution. So in this scenario, if this is our distribution here, this would be actually quite difficult to calculate. We could estimate it. We could get pretty close. Okay, but what is the area of this? Well, if you wanted to take a good guess at it, it'd be kind of similar to this box. Okay, I've kind of met in the middle here. It would be similar to the area of this box. What's the area of that box? Well, it's the width. This width is 5 times the height. We would have to calculate this height. We could do that, but if we know the formula here. Okay, so we're not going to do it with this exact distribution. We're going to do it with some other, the specific ones, the uniform, the normal. But this is the process that we would do. We want to find the area of this rectangle. Okay, so we would multiply 5 times whatever this height is, 0.07 or something. That would be too big, but 0.012, I don't know. And we would be able to find that exact area. So people that have taken calculus, this is going to feel very natural to you. Okay, if you haven't, that's not a problem. As I said, we're not going to actually crunch it here. But this is integrating, right? We take a good guess, we estimate, we get smaller and smaller and smaller, right? Not to give you flashbacks from your calculus days, but that's what we're basically doing here. We're adding up the size of these slivers until we get a good estimate of that. And that's why we would need to know the exact formula of this distribution. So that would be the process. As we'll see, we're going to deal with some some distributions that either have really easy calculations or the work has been done for us. So first, let's turn to one that is the easy to work with. And that is of the uniform distribution. Okay, so we're going to leave our discrete case behind, and we're going to look at the uniform distribution. Now we're going to talk about one example, and this is going to be similar to the one in your book. And the reason for that is that it's hard to come up with different uniform distributions because they don't exist in the real world very often. So when we talked about binomial distributions, they're used quite often. They're pretty powerful. Uniform distributions, it's a good way to wrap our heads around what's happening, but don't expect that you're going to be able to put everything into this type of a distribution. A uniform distribution simply means that it's the same. Okay, so I'm gonna alter a little bit from your book. Your book talks about from 0 to 30. Just to give you a different outlook, I'm just going to talk about from 5 to 35. And so this is bus arrival. Okay, and this is kind of the only scenario, or one of the only ones. So imagine that we know that the bus comes every 30 minutes, but we don't know when exactly it comes. There's no defined time. It doesn't say at 11:12 it's going to show up. We just know that it is going to come every 30 minutes without fail, but we don't know exactly when. The only other thing we know is that we can see, maybe we can see down the road 5 minutes, so we can see a few bus stops away. So we know it's not coming within the next 5 minutes, but that's all we know. We know it's coming somewhere between 5 and 35 minutes. So because we have no other information, our best guess or our best thought is that it's evenly distributed. And that's really what the uniform means of this. So when we have something this simple, the math isn't too cumbersome. So let's talk about what we'd like to do. We'd like to summarize this. So we're going to talk about how to calculate the mean and the standard deviation. We're going to talk about how to calculate the area of a certain range, right? That's what we're after. We can from this information we can calculate the likelihood that it arrives somewhere between 7 and 12 minutes. So sorry if you're writing down, following along. I'm gonna change the numbers a little bit so that it is different than the book one, so that if you do want another look at it. So I'm gonna actually say it's every 20 minutes. So it's between 5 and 25 minutes. And that way you'll be able to see at least 2 examples of this. So if it's, again, now we know that it's coming somewhere in the 20 minutes. We can see 5 minutes ahead. So we know it's not in the next 5 minutes. So it's between 5 and 25 minutes. So with that in mind, there are some things we can quickly calculate from this. We would like to find the mean of this. So what is the mean? Well, the mean of this area, and we don't have to, with something this simple, we probably don't even have to calculate it, right? Where's the middle of this situation? Well, it's going to fall right in the middle. Because this is uniform, it's symmetric. Right? So halfway in here is 15 minutes. So if you had to give a kind of a center guess of your data, it would be at 15 minutes. But we can calculate this, and it's useful to know the formula. So when we think about uniform distributions, we label them A and B as our 2 endpoints. Okay, so if we've done that, the mean is just simply A plus B divided by 2, right? That's how you find the middle of any 2 points. So that's A plus B would be 5 plus 25 divided by 2, which is 30 divided by 2, which is 15, okay? I know we can do that without the formula, but this can be helpful if it's a more complicated scenario. So when we then turn to, so we're going to do standard deviation in a second, but we're also going to talk about finding the range, right, the probability of falling within a certain range. So to do that, we're going to want to know the width, but also the height. So how do we figure out the height of this rectangle? Well, we can rely on the fact that this total area sums to 100%. Okay, and so we're going to use the height then must be equal to 1 over b minus a. Because we want, this falls out, so you can just kind of memorize this, but notice that this is going to fall out of 1 is equal to the height times b minus a. Right? This area of this rectangle is b minus a times the height, and it must equal 1, right? 1.00, 100%. So we just rearrange that and say height, we divide by b minus a, and that's how we get this, okay? So we plug that in. The height is 1 over 25 minus 5, 1 over 20, okay? In your book, it stretches from 0 to 30, and so it's 1 over 30. So this height here is 1 over 20. Again, the probability, is that on the screen? It might be off the screen. It says 1 over 20. So again, the probability that it arrives exactly at 15 minutes is still 0. But if we give a range, now we have a way to calculate it. So if we want to say, what's the probability that arrives from 17 to 19.5? This might not be drawn to scale, but if we want to know the likelihood that it falls in between those two values, 17 and 19.5, we simply need to calculate the range, or the area of this rectangle. Again, because it's a uniform distribution, we have nice clean rectangles. The math is quite simple. So we can simply do that by, we can just do, we need height times the width, which is, the height is 1/20th. Again, it's the same all the way along. That's why the math is so simple here. 1/20th times 19.5 minus 17. This is 2.5. And so we get 2.5 over 20, which is, what is that, 12.25? 12.5? I'm going to say 12.5. You can double check my math. So there's a 12.5% chance, or a 0.125. Is that right? You can verify. So there's a 12.5% chance that the bus arrives between 17 and 19 and a half minutes. Okay, that concept of adding up, finding the area under the curve, is what we're going to do this whole time. And we're going to do it a lot when we turn to normal distributions. Okay, it just so happens that this is the simplest math that we can do, because it's a nice clean rectangle, and we always know the height. I also said we'd do the standard deviation. Let's see what kind of area I can have. So the standard deviation, and we won't derive this formula. We'll just hope to find some area for it. So the standard deviation of a uniform distribution, sigma is the square root of b minus a, right? So the same b minus a squared divided by 12. Okay? That seems like a very random equation. If you're curious about, where this falls out of, we can talk about it in office hours. But also, if those types of questions interest you, it might tell you, maybe look more at like an econometrics course, or some deeper, take another statistics course, because we would talk about how we find that exact formula in econometrics. But this will give us the standard deviation, right? How spread out our data is. This is just for the uniform distribution. Okay, if we're over here, we have to do a different type of calculation. But the math is nice and clean with the uniform. Okay, and you can, so b minus a, so this would be the square root of 20 squared divided by 12, square root of 400 divided by 12, which is the square root of, 30? Do I have that right? I don't know what the square root of 30 is. 5.4? I don't know. But that would be the standard deviation. So we could talk about this as having a mean of 15 and a standard deviation of whatever the square root of 30 is. Okay, and we can also focus in and say there's a 12.5% chance of being between 17 and 19.5. Okay, because we're talking about a range, that includes all of those intermediate values. Okay, so notice if we're in the more complicated scenario, these simple calculations, this height times width, is not going to work because while we took a guess here, we don't know the height at each of these points. Okay, and again, we'd have to rely upon integrating, and you can do this, people do this with these types of probabilities, but it's very cumbersome, and so we're not going to do it here, and it's not done that frequently. right? But again, we could integrate from 65 to 70, but we'd have to know the formula, right? It'd be x to the, maybe 3x to the fourth minus 2x cubed. I have no idea what it would be. Some gross formula. So setting that aside, let's move to the other big family of distributions that we're going to talk about. This family is also not as clean as this one, right? This is very specifically chosen because it's nice and easy to deal with mathematically, and we can see what we hope to do. We'd hope that they're all this easy, that we can find these nice, clean calculations. So shifting our attention to the normal distribution. And like I said, the uniform is kind of, it's only there, we only learn it because it's so nice for the math. We don't use it a lot in practice. On the flip side, the normal distribution is used extensively in statistics. Okay, and we're going to be carrying with us this understanding of the normal distribution the rest of the semester. Okay, we're going to spend a lot of time with it. So this process that I'm about to talk through turns out to be pretty important. So what I want to highlight at the start is that the normal distribution is a family of distributions. There is no the normal distribution. There is a normal distribution out of many normal distributions. Okay, so for instance, let me get a little more room. We could write a normal distribution that that centers at 65, okay, and has a standard deviation of 4. Okay, that is a normal distribution. So we could also draw another normal distribution that is drawn better. That's somewhat normal. Okay, it's supposed to be nice and normal. Okay, this could have a mean of, actually, let me rewind. Again, I apologize if you're writing in pen. I want the first one to, you'll see why in a second. I'm gonna have this first one be centered at 70, and this one be 65. Okay, so the red one, if those show up differently, is going to be 65 with a standard deviation of 3.5. Okay, those are both normal distributions. These are two of the family of normal distributions. So what makes a normal distribution? Well, there's a few characteristics that I want to highlight. They're bell-shaped. Okay, what this means, you know, visually, it's we've seen these before, and they have this familiar kind of bell shape where they curve up and they curve down. Now, mathematically, we have parts of convex and concave all mixed in there. So there's some more mathematical context here, but really they bend up quickly and then they kind of tail off and smooth, and then it all of a sudden takes off again. Okay, so that gives it kind of that kind of double bend bell shape. More importantly for us, or for what we're going to do with it, is they're symmetrical. Okay, so ignore the fact that I can't draw very well. These are supposed to be symmetrical, and that's going to be incredibly useful. Another way, another thing just to recall from previous chapters, that means there's a skew of 0. But symmetry is going to be important. So just like in all of the previous, this had the sum of this whole area was 100%. The sum under a curve, okay, so just think about the black one here. The sum under the curve is 100%. Because they're symmetrical, that means there's 50% on either half. Right? So half of the likelihood is below the middle, which Again, skew of 0, symmetrical, that means the median and the mean are 70. So half of them fall below and half fall above. That's going to be really helpful. It's one of those. It's going to be kind of a trick or a shortcut that you're going to be able to use with some calculations, and we rely on that fact heavily. And then lastly, there's another one. They are asymptotic. Okay, not asymptomatic. Those are similar words, but if you're on Twitter and a doctor gets them confused, it's because I don't know why, but they are asymptotic, meaning they never touch a certain value. Okay, asymptotic, just a fancy mathematical term to mean they approach a value but never touch it. So in this case, that value is 0. So as they bend down, they flatten back out. They keep getting closer and closer to 0, but they never actually touch 0. Okay, the same thing is over here. Obviously, sometimes when I draw them, they touch 0, but they're not supposed to. Okay, so that is a normal distribution. It has these characteristics. And again, what I want to highlight is that there's a whole family of distributions. Much like this uniform distribution is a uniform distribution. The one in your book stretches from 0 to 30. It's also a uniform distribution. All of these sum to 100% underneath. All of these sum to 100%. So again, under the black is 100%. Under the red is a different 100%. What distinguishes these two is that they have a different mean and they have a different standard deviation. I could draw another, I could draw one out here. Let's say that has a mean of 94, and this has a standard deviation of 4. Okay, it looks about the same. I tried to draw it the same as the black, just shifted over. You can see that they're both the same kind of fatness. The red one here is smushed up. It's skinny and tall because the data is not spread out as much, right? So standard deviation is measuring how spread out our data is. So we have a slightly smaller standard deviation. We have a tighter and taller distribution. Okay, I probably, that's a little more extreme than just a 0.5 difference is, but it's kind of to highlight the concept that a smaller standard deviation is going to be a tighter and taller distribution. It has to be taller, right? If we're going to tighten it up, it's got to push up because the area under it still needs to be 100%. So we're going to get familiar with dealing with all kinds of different normal distributions. They're all going to look somewhat similar to this. Okay, so how do we depict or how do we talk about normal distributions? We use exactly what we've been talking about this chapter. We want to find a good marker. We want to express it with our two big terms. So we often will write it as n, and then we'll list the mean and the standard deviation. Okay, so the black distribution here is a mean of 70 and a standard deviation of 4. So that is enough information to tell me that I want to draw or work with this black distribution here. Okay, similarly with the red, I would simply say this is a normal distribution, mean of 65, standard deviation of 3.5. So we've kind of gone the opposite direction. I already knew what these were. So we're not calculating them directly, but we could calculate them. We could also, so what's the big thing we want to know? We want to know what's the likelihood of certain outcomes, right? We wanted to know 17 to 19 minutes. Here we might be interested in certain ranges of outcomes as well. I'm going to erase the orange here. I want to focus in just on the black and the red. The black and the red distributions are the two distributions of height, I believe of American. So the black is American male adults, and the red is American female adults. And those are a pretty good approximation of the distribution of heights. Now, we'll talk in Chapter 8, we'll discuss something called the central limit theorem and why we can use the normal distribution all across statistics. One place it naturally comes up is in biology. So biological functions tend to have, or oftentimes have, normal distributions to them. So things like height, weight, arm length, claw length of a crab, things like that. So we can often use those to play around with normal distributions. So similarly here, we have two distributions, one for males and one for females. They both have a normal distribution. We can think about finding the range of certain probabilities. So for instance, you have a child. What's the likelihood that they grow up to be somewhere between, maybe you want 72 to 76. Maybe maybe you're still going to, so this would be a male. Maybe you're still going to think about football as a activity, and that's the best range for a quarterback, and that seems to be the safest position. I guess maybe kicker. So you want to know what's the likelihood that this American male grows up to be between 72 and 76. I think nowadays this is pretty standard across almost all countries. There used to be larger differences, mostly attributable to nutrition. So we want to think about a range of outcomes, right? Just like we wanted a range here, now we can think about probabilities that they fall somewhere along this range, right? Because again, they may not be 72.5, they might be 72.463, okay? So we're going to talk about ranges. So how do we go about this? Well, we would have to integrate over this formula, or over this equation here. So I'm going to write out the equation for the normal distribution. It's going to look very gross. It's also in your book. You don't need to memorize this. We're never going to crunch it, any exact value of it. But this is what it is. It's 1 over sigma, right? So the standard deviation, square root of 2 pi e to the negative, here we have x minus mu squared, okay, that should look familiar, over 2 sigma squared, or the variance. Okay, so that is the equation for a normal distribution, or any normal distribution, if we plug in the mean and the standard deviation, right? So we have to give the mean and the standard deviation. You can see them showing up here. So we have standard deviation. It shows up again as the variance. And we also have the mean up here, okay? So very gross, very cumbersome to work with. Now, I do want to point out that you know everything in here, okay? So we just said mean, variance, the standard deviation, the variance, the mean. Notice what this is. X minus mu squared. You're probably sick of calculating that, but that is the standard deviation, the deviation from the mean squared. It's in our calculation of standard deviation. Okay, and then the other two things in here are the pi and e. Now pi, confusingly, we've switched back, and this is actually 3.1415926. Let me test myself. 535, 7879. I don't know. E, I'm not going to get nearly as close. Something like 2.718. Okay, these are just two mathematical constants. Okay, so you understand already everything that goes in here. Now, it doesn't mean you want to actually go through the process of dealing with it. But what it means is that if we plugged in 70 and 4, and then we wanted to say, what is the value at 72? all we would do is plug in 72 for x, and it would spit out that value. It would spit out whatever this is. Okay? So again, mathematically, what we would do to find the area is to do that for every point, or that's really what integration is doing for us in some sense, is to find smaller and smaller little windows, add all those up. Again, you can do more of that in calculus. So what I want to say is that that is possible, and in fact, you could do that. You could integrate from 72 to 76, and you would find the area, maybe it would spit out at 24%. But you'd have to do that for this. You'd have to re-plug in and redo it if you wanted to do from 73 to 76 or 74 to 79. You'd have to do it new every time. You'd also have to do it new another time if you wanted to switch and talk about females, right? A female could also be between 72 and 76, or 61 and 71, right? So for every new range and every new distribution, we'd have to go through the process. So what I'm trying to get to is this has been done for us, okay? So we can skip this whole process of integrating if we make one simple transformation. What we're going to do is we're going to take any normal distribution, these two included, the orange one we had, any normal distribution that we can think of, we're going to take it and transform it into one standardized distribution. And again, this seems very cumbersome and weird at the start, but trust me that it's going to be helpful. So what we're going to do is we're going to use a blue marker. We're not going to use a blue marker, so we're going to go back to just black. We're going to take all of those distributions and we're going to consider them. We're going to think about what if instead we were talking about a distribution that was centered at 0 and had a standard deviation of 1. Okay, this is called the standard normal distribution. Now, again, the whole process or the whole reason for this is to avoid all of this gross math. We're going to go and use this distribution. What do we mean by that? Well, let's think about, so what really is 72? In this black distribution, 72 is 2 inches larger than the mean, taller than the mean, right? It's 2 more than the mean. Another way to think about it is that it is 1/2 of a standard deviation more than the mean, right? It's 2, and the standard deviation is 4, so it's 1/2 of a standard deviation. And that's the calculation we're going to do. We're going to turn everything into what we call z-scores, where z is x minus mu. Okay, this is just a deviation. Notice we're not squaring it this time. So we do want to know if we're below the mean. So something like, 63 is going to be below the mean. It's going to be a negative number. So x minus mu divided by sigma. That's our z-score calculation. In this case, z, we'd say 72 minus 70 divided by 4 is 1/2, or 0.5. Okay, so what that means is that this is 0.5. Standard deviation is more than the mean. That's the same as thinking about, 0.5 right here, right? 0.5 is 1/2 of a standard deviation more than the mean. That's why we use this very simple 0 and 1, is that they're quite easy. We can put the z-scores right on here. So this is, you could also think of this as a z distribution. Okay, a few more steps here to highlight. And we'll spend some time on Friday playing around with this and doing the exact calculations. But I want to get your mind in that mentality so that you can start digging into the material, and this won't come as much of a shock. So 1/2. What is the 76 z-score? So we could even just list 72. Z of 76 That is 76 minus 70 divided by 4, which is 3/2, right? 6, it's 1.5 standard deviations. So we could even just say 1.5. Okay, it's 1.5 standard deviations. Now, here's where the magic happens. The share of this distribution, remember this is all 100% under the black one here. The share of this is a certain percentage, right? This window here, if we were to integrate and do the crazy math, we'd get some percentage. I think before I said maybe it's 24%. If this is 24%, I should have maybe just checked the math there, but let's say that's true. This is also 24%. Or more generally, this is the same share as this window, okay? And that's true across all normal distributions. So the area under the curve from 1/2 a standard deviation to 1.5 standard deviations is some percentage. And that is true for all normal distributions. So that means we can take any normal distribution, figure out the z-score of 2 values, and then think about what it would mean over here. So that by itself isn't that helpful, except remember to calculate this, we'd have to do all the math. So we would have to do the math here. But somebody already did it for us. Okay, and that's the real trick, is that this math has already been done. So somebody, a lot of people, but somebody has gone through the pain of calculating all the different values that it could be for each of these, basically each of these windows. And we can look that up in a table. And so in your textbook, there's an appendix, and you can look up the exact values of certain windows. I've also posted it, I think it's called Z-Table. It's on the Chapter 7 module. So we can just quickly look up. So basically, if you want to say, what's the chance that this person grows up to be between 72 and 76? The process is, crunch them into z-values. That means they're here on the z-value or the z distribution, and we can just look that up in the text. Now, one last thing to realize is that if we wanted to list out all the possible relationships, we'd have to list 0.5 to 1.5, 0.5 to 1.6, 0.5 to 162, and so on. We'd have to do 0.6 to 1.5. There'd be a whole list. So, to make that easier, or to put it in just one table, the z-table is organized, and the way that we think about it is we're not going to directly say 0.5 to 1.5. What we're going to say is, what's the chance that it's between 0 and 0.5? Right? There's some chance that you're between 0 and 0.5. That's the same chance as between 70 and 72. Okay? So that's some percentage. We'll walk through an exact example of this on Friday. There's also a chance that you're between 0 and 1.5. So we're going to list that in the book. Okay, but notice that's a much larger sliver. And so how do we find 0.5 to 1.5? We take the larger 1.5 and we subtract off the 0.5. Okay, so there are a few steps to this, and it'll make more sense when we walk through examples. But hopefully, and maybe, you know, I don't know your study habits, but this might be a good lecture to return to after Friday when we've walked through it again, and maybe this will sink in more. But that's the process. That's how we handle normal distributions. Okay, and again, I know it seems very cumbersome for just this one random set of distributions, but let me assure you that these are used extremely heavily in statistics, and we'll use it the rest of the way. You know, vaccine trials that are out there relying upon normal distributions of various outcomes. How likely is it to be that far off in the normal distribution? Okay, so we're really focused in on tail events, but it is all based around the normal distribution. So becoming familiar with this is quite helpful. Okay, so we'll leave it there. Again, barring any technical snafus, this should be posted later today. You can also look again for an email from me later about grades, And otherwise, we will see you on Friday virtually.